Hi everyone, we're going to continue with this preview example and do something that's a little less preview. So we have conjectured a formula. So let's see, we were working on this function. We have f of x equals 4x minus x squared. And we've conjectured that f prime of a is equal to negative 2a plus 4 just by working through a bunch of derivative calculations and recognizing a nice linear pattern there. So I want to walk through a little bit more general way to find a formula like this. Sometimes the patterns in derivative values are a lot less obvious, so it's going to get really tricky to guess an equation. So really all it comes down to is going back to if you want to find a formula for f prime of a, we already know how to get that. We take the limit as h approaches 0 of f of a plus h minus f of a all over h. And the way to make it a formula instead of just giving one slope is just to leave the a in there. Don't be specific about which x value, leave that as a variable and choose the a after the fact. So in this case, we're going to get the limit as h approaches 0 of 4 times a plus h minus a plus h squared minus f of a, which is 4a minus a squared. Okay, so one more time through this. If you work through all of those preview examples, you're probably really tired of seeing the same work, but one last time through. And again, when you're doing these, absolutely you should be expecting to have to show me some work through limit definitions on a test, and the work itself is really important. I need to be able to see your process. The point is to explain to me how you know the answer is what it is. So really careful about writing the limit down every time and making sure I can see exactly what happened. Okay, so I have a 4a plus 4h distributing just like before, and then I'm going to FOIL. That'll give me an a squared plus 2ah plus h squared. And then here I'm going to go ahead and distribute the negative sign. That's a new step because before we had just, at least I had just in my head, figured out the value of f of a. So it will become a minus 4a plus a squared all over h. And then we can distribute that minus sign through, or if you're comfortable, we can just look at this and say, okay, well, then this is going to become a minus a minus 2, a minus h squared, which means some nice things are going to happen. Let's see, the a squared, negative a squared plus a squared, that goes away. The 4a minus 4a, that goes away as well. Do I lose anything else? No, I don't think so. So I have the limit as h approaches 0 of 4h minus 2ah minus h squared all over h, which as we factor an h out will allow us to cancel. So that's rather perfect. And there's some familiar things starting to show up. Okay, so we factor, we cancel, and then with what's left over, we want to let h go to 0. So this part's actually dropping out. But h going to 0 doesn't do anything to the 4, and it doesn't do anything to the minus 2a. So there's the exact same formula that we got before. And really, there's no reason for us to call our x value something other than x. In the function, we called our x value x, and in the derivative, we can as well. So generally, you just see this in calculus because we first want to build up that idea of the derivative at a point. So we're really specifically using a as a given constant, a given value of x. Whereas here we're saying whatever x value you want, go ahead and plug it into this formula and it will give you the slope of the tangent line. So the fact that I used a is completely arbitrary and unnecessary. You can just keep it as x. And that's what we'll do to emphasize that now we have a new function And this function inputs the exact same thing as the original function, x, and it outputs slopes of tangent lines. Okay, so let's see. I think I want to sneak in a definition here. Let me just think if I'm forgetting anything else I want to say. I don't think so. Okay, so a little definition of the derivative. It's not very drastically different from what we already have. So this section is really just about a shift in our thinking. A lot of the algebra and stuff will be very similar. A little bit messier because we'll have two variables, but really similar. So definition of the derivative function. So I'm going to say for any x in the domain of f, we define the derivative function and that is going to be, there's two different possible notations, f prime of x or the derivative of y with respect to x, dy dx. And here we would be thinking that y is another name for our function. So y is what our function outputs. Okay, so either of those notations mean the derivative function. And notice that I'm not putting any value 8 at bar. This is the general derivative function y with respect to x. And the way we'll calculate it is to use our limit definition, but not choose an x value ahead of time. So this is now building up a derivative function that we can tell our x value and it will tell us our slope, which is kind of reversing the process we had where we would first pick our x value and then we would crunch through the limit and then we'd have a slope. And if we wanted the slope at a different point, we'd have to go through the limit definition again. So this just does the limit definition in a very general way, and then it's just plugging x values into an equation. Excuse me. Okay, so last little thing to talk about here is just again about the picture. We're going to look at this graphically a lot. So what we just did was figure out what the derivative function was algebraically. We got a perfect equation for our derivative function. The graph thing is sometimes a little less perfect. There's some approximation that happens, but it is also really important. So basically what we're saying is we started with our function. This is our y equals f of x, or y equals 4x minus x squared. And we've just created a new function where what we do is we say, okay, well, what if my x value is 0? And I draw a tangent line, and we've already calculated the slope, so we don't even have to estimate that. We actually know from our work on the very first page that the slope is 4. So what we're doing with the derivative is saying, okay, if we input that exact same x value, we output 4. So this is 0.00, which is an xy pair. This is 0.04, which is an xm pair. Same x value, but our y value is now slope. And if we watch this function, what happens is we start with really big positive slopes, and then as x increases, the slopes start to level off and then hit 0, and then become negative and more negative and more negative. So we should definitely see some sort of big positive, smaller, 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 0, negative, more negative. So that's making sense. And then the fact that this is perfectly linear is really just because this is perfectly quadratic. We could have a similar shape that wasn't actually quadratic and it wouldn't be a perfectly straight line. So again, if we go to m equals 2, the function goes through the point 2, 3. At the point 2, 3, our slope is 2. I'm lying to you, I'm sorry. This is the point 1, 3, x equals 1. So our function goes through the point 1, 3 with a slope of 2. Our derivative doesn't tell us anything about the 3, but it does tell us the slope. So again, this is x slope. And then at x equals 2, the function is going through 2, 4, but the derivative will go through 2, 0 because the tangent line there is horizontal. So at any one of these, when I say m equals -2, I'm saying the slope of this line is -2, which means I'm talking about f prime. So this is f prime of 3 equals -2. And again, you'll see that x value and then the slope. Okay, so we'll want to work on this graphically as well. And there's just a first example of that where we already know a lot of the info. Thanks for watching.